in the last lecture, we learned about the a chain with 2 atom bases. So, let me summarize those results. So, we have now a situation where we have a 1D chain with 1 atom basis, which is the monoatomic chain. So, these are the Bravais lattice points, and then the atoms can be found at some position out of the equilibrium. So, this is the atom at the nth site. So, this you have already learnt. So, for instance, this is x sub n, that is the position of the nth atom at any time t. And we learnt that the dispersion for this chain between minus pi by a and plus pi by a. So, these are the boundaries of the first build one zone, and the dispersion that we worked out, it looks like this: omega equals under root 4 k by m, where k is the spring constant, the stiffness of the bond that keeps this solid together, and then modulus of sine of little k a by 2, where little k is the wave vector which we have plotted on the x axis over here. So, this is little k, and omega is plotted on the y axis. So, these are the frequencies of the normal modes that you would excite on this lattice, and the dispersion looks like this on the two sides. Okay. So, that was for the monoatomic chain. Now, coming to the diatomic chain, so herein we have once again the same Bravais lattice as before. These are the Bravais lattice points that are marked with crosses. The distance between any two Bravais lattice points is a, same as before. But in this case, we are going to decorate each lattice site with 2 types of atoms, as we did in the last lecture. So, we have atom A, whose mass is Ma, m subscript A, and then the mass B, which is shown like this. Okay, and then the spring constant, which represents the intramolecular force, this is given by K prime, and the force between the two molecules is K. Okay. The masses here are m sub A and m sub B. So, for this case, the dispersion relation that we derived, we saw that in the dispersion relation there are actually 2 branches. So, once again, going from minus pi by a to plus pi by a, the zone boundaries, and then the interesting aspect of the diatomic chain is that for each value of k, there are 2 values of omega, and these values are given by omega plus and omega minus. So, I am writing a single equation for both of them, and this is given by k plus k prime divided by m plus minus, where plus sign is for the plus sign over here, omega plus, and minus sign is for omega minus. And then you have 1 by m times square root of k square plus k prime square plus 2k k prime cosine of ka, right? So that you remember. So the important point is that here you get, so this square root is k square plus k prime square plus twice cos little k a. So it's a function of the wave vector k. So the wave vector dependence comes over here because everything else is otherwise constant. The mass of atom is constant, and we have assumed that the mass of A is equal to mass of B. So these two atoms have same masses, so they are in principle identical atoms. What is different here is that the spring constants are different, the stiffness is different, the stiffness of the intermolecular and intramolecular forces. So everything else is constant, so omega depends only on the little k, the wave vectors, and for every value of k, for each and every k, you get two values of omega. So the omega minus, we did this in the last lecture, omega minus looks nearly the same as omega in the case of monoatomic chain, but then the additional branch that you get is the omega plus, and that branch looks like this. Okay, so this is omega plus over here, and here is omega minus. And if you want to know how we plotted this, how we got these plots, I mean a little more detail of plotting this, you should look at the last lecture. So these frequencies, so here is 0, 0, and we also showed in the last lecture that omega minus approaches the zone center linearly, which is the same property as this mode had. In this case, it's more easily, it can be more easily seen because for small values of k, sine of ka is just ka by 2, and therefore omega has a linear dependence in k. In this case, it's a little difficult to see, but you can simplify it and see it yourself. So the value over here, this value, which is the cutoff value, is square root 2 k by m. The value over here is square root 2 k prime by m, and the value over here is square root 2 k plus k prime by m. Okay, and in the last lecture we even justified in a way why we get k and k prime both for this point, and why do we get k prime for this point and k for this point, by analyzing the relative motion of the motions of the atoms for these modes. All right. Now, if you take any of these, either this one or that one, let's take this one for simplicity. So you know that on the x-axis we have very closely spaced k points. How closely spaced are they? So for that you have to look at the possible values that the k can take, which you derive using the periodic boundary conditions. So the little k which you derive using the periodic boundary conditions is given by 2 pi over a times capital N and then times some integer m. So here is some integer, let's call this integer as s. So s is an integer, so I will write it as k sub s. So these are the possible values that the k can take. And since, what is n here? N is the number of lattice points, okay? And the number of lattice points is very large because we are dealing with a crystalline solid, all right? So in real life, n is of the order of Avogadro's number, okay? So you imagine you have, you have Avogadro's number of k points in this region, in the space from minus pi by a to plus pi by a or 2 pi by a. So if you zoom in this curve, if you look at the zoomed in portion of this curve, so how would it look like? So let's say you have zoomed in by a factor of 10 to the power 10, where n is also of the order of 10 to the power 10, then you would see the distinct points. So you would see a point here, a point over here, a point over here, a point over here, and these points are essentially the points on this section of the dispersion. So each of these points is an ordered pair, okay. So its x coordinate is ks and its y coordinate is the corresponding omega of that ks, okay. So let's call it omega sub k sub s, okay. Then you go to the next point, and when you go from point here to point here, how much does the k change? The change in k in going from here to here, this little step, this is delta of k, this is nothing but, you can get it from here, so it will be s plus 1 minus s, so that will give you 2 pi over a n, all right. So on the x-axis, the spacing between the x coordinates of all these points is a constant, which is given by this number. But on the y-axis, because this curve is non-linear and it's flattening as you go towards the zone boundaries, therefore the omega points will get denser and denser. So as you go up, the omega spacings will get closer and closer. But those are just the matter of details. The whole point is that this is not a continuous, but the way I have drawn it, it looks continuous, but it's actually quasi-continuous. Quasi-continuous because the number of k points between minus pi by a and plus pi by a is huge, is very, very large. So therefore, the spacing is very, very small. So why did I say this? I said this for a very special reason, which I will reveal now. So let's go back to the dispersion for the diatomic chain. In the diatomic case also, you will see the same thing. If you zoom in any region of this dispersion, you would see points, and similarly you would see points over here. So for every k, there are two values of omega, right. So let's now redraw that dispersion, because I want to show you something special. So here is the center, here is the point, let's say 2 pi by a. You know what 2 pi by a is? What is the importance of 2 pi by a? 2 pi by a is the first point on the reciprocal lattice. So the reciprocal lattice vector, g vector in our notation, is given by 2 pi by a times an integer. Let's call that integer once again little x, x cap. So when s is 0, you are sitting here. When s is 1, you are sitting here. And when s is 2, you are sitting here, and so on and so forth. Okay, so what's the big deal? Same thing you can do on this side. You get minus 2 pi by a and minus 4 pi by a, and so on and so forth. Okay. So how do you find the first Brillouin zone? What is the definition? The first Brillouin zone is the primitive unit cell or the Wigner side cell of the reciprocal lattice. And how do you get the Wigner side cell? To get the Wigner side cell, you have to connect the nearest neighbors to the central point and take the perpendicular bisector. So that's what we are going to do now. I just want to make sure that I have drawn them at equal spacings. So let me keep this consistent, because I would be, what I am going to do next would look nice if the distances are maintained. So you want to draw the first Brillouin zone. So what would you do? You will take a perpendicular bisector here at plus pi by a. So you take perpendicular bisector plus pi by a, you get the line for the first Brillouin zone, and minus pi by a, you get the line over here. That's your first Brillouin zone. And I'm going to write it as 1 for the first Brillouin zone, and I'll write 1 plus for to indicate that it is on the plus, in the positive half of the wave vector space. So here the wave vectors are all positive, and here the wave vectors are all negative. So that's my first Brillouin zone. Now, where is the second Brillouin zone located? In order to get the second Brillouin zone, what do you have to do? You have to connect the central point to the next neighbors. Next neighbors, I mean. Next neighbors. So this is the nearest neighbors, and this is the next nearest neighbor. So you connect it here, and take a perpendicular bisector. So, where would that perpendicular bisector come? It will come up here at minus 2 pi by a, and similarly in this case you take the next nearest neighbor which is sitting at 4 pi by a, and you take the perpendicular bisector which is sitting here. So, that is here. So, where is the second Brillouin zone? So, the second Brillouin zone is the space between these two yellow lines, excluding the space which is already occupied by the first Brillouin zone. You cannot take that anymore. So, therefore, what are you left with? You are left only with the space over the region from here to here and the region from here to here. So, I am going to call this in my notation as 2 plus and this as 2 minus. All right. So, this is my second Brillouin zone, and then you can go to the third Brillouin zone and so on and so forth. Now, let us try to redraw the dispersion for the diatomic chain on this graph. So, this is the branch, lower branch, which is called omega minus, and here is the upper branch, which is omega plus. Good. So, let me use two different colors. So, I'll tell you what exactly I have in mind. Give me 1 minute. Okay. Now, what I can do is I can take any k point over here. You know that I just now told you that this dispersion is nothing but a sequence of k points, k omega order pairs. So, you can take a point over here, for instance, and what you can do is you can add 2 pi by a to it. So, what will happen? You will go into the second Brillouin zone, okay, and that point is exactly the same as this point over here. They represents the same wave, okay. So, if I add 2 pi by a to this pink section, I will be able to transport it into the second Brillouin zone, and that is what I am going to do. So, I am going to transport this. So, this section has been transported to the second Brillouin zone by adding 2 pi by a to every point, every k point. So, you add 2 pi by a to this point, where will you end up? If you add 2 pi by a to this point, you will end up here. If you add 2 pi by a to this point, you will end up here, and similarly for the intermediate points. So, you have transported this branch to the second Brillouin zone. Now, what else can you do? You can transport this branch which lives in 1 plus, you can transport this branch into the second Brillouin zone, the negative half of the second Brillouin zone, by subtracting 2 pi by a, which is once again the lattice vector, and you are perfectly allowed to do this because you are living in a crystalline lattice which obeys the translational invariance. So, therefore, I have now transported it over here. All right. So, I can now remove these because they are already, I have already copied them into the second Brillouin zone. So, I do not need them here anymore, they are already copied. So, the same dispersion which I showed here has been shown over here, except that now I am using the second, the zones beyond the first zone. Now, this kind of representation is known as an extended zone scheme, and you will use it, you will see it very frequently. In fact, when we will go to electron transport, you would see it very, very frequently. We will switch from the extended zone to the conventional scheme, and this conventional scheme is called reduced zone scheme because everything has been reduced, all the branches have been folded back into the first Brillouin zone. So, this is called reduced zone scheme as opposed to the extended zone scheme shown over here. So, what is the point? Why should we have extended zone scheme, especially for this lecture? What am I driving at? So, look at this diatomic chain. In this diatomic chain, what is the lattice spacing? A. Just as the lattice spacing here is A. What is the distance equilibrium separation between the basis atoms. You remember the previous lecture, the equilibrium separation between the basis atoms is little d, right. So, let me redraw it. So, this is my basis, and the separation between the basis atoms is d. Now, we take a special case where this d is equal to a by 2. What will happen if d is equal to a by 2? Okay, you can make d equal to a by 2. In that case, here is your lattice, here are your lattice points, which are again shown with crosses, and here are your basis atoms, which are shown right now at the equilibrium position. So, it is like this, right. Now, if d happens to be equal to a by 2, what is going to happen is that this spacing is a by 2, all right. Then wait a minute, let me redraw it more properly. So, here is your yellow point, and then the cross, and then the blue point at the same distance. All right. So, the distance here is a, and the distance here is a by 2. Okay. And this again is a by 2. Okay. Actually, this is d, but I am saying if d is equal to a by 2, then what will happen? So, if d is equal to a by 2, okay, and if the masses are same, if mass of a, which is already the case actually in our derivation, mass of a is equal to mass of b, and this is equal to a m. Okay. And if I put an additional one more condition, which is that k prime is equal to k naught, let us say. Now, what is going to happen? Not equal to k, right. If you make k prime equal to k, this gap will disappear. Okay. So, this gap will disappear, meaning this pink branch, the omega plus branch, will come down, all right, and merge with this point. Okay. So, this branch will then come down, and it will look like this. And similarly, this branch will come down, and it will look like this. Okay. So, the new lattice spacing is a prime, which is equal to a by 2. So, if you write this as pi by a by 2, and this as 2 pi by a by 2, and same thing over on this side, and then you can replace a by 2 by a prime, and similarly here you can replace a by 2 by a prime. So, what have you achieved? What you have achieved is that in the new lattice, whose lattice spacing is a prime, these two branches, omega plus and omega minus, will merge to give you exactly what you had here for the monoatomic chain. That is the point. That is why we did all this, in order to prove that the diatomic case will merge into the monoatomic case if you set k prime equal to k naught, because the lattice spacing will then reduce to a by 2. It won't be a anymore. Okay. I'll keep this. I don't even need this, but I'll use this part of the board to make the second point. So, here is the dispersion for diatomic chain. If I have to draw here the dispersion for electromagnetic wave of frequency omega, right. So, for electromagnetic waves, you know that the omega versus k relation is rather simple. Omega is equal to c times k. That is the relation, dispersion relation that the electromagnetic waves follow, where c is the speed of light, right. So, this number c over here, you know this number is a very large number, okay. And if you look at the dispersion for the lattice waves, and if you draw a tangent over here, this tangent line, then you know that the slope of this tangent, which is omega d omega by dk, this d omega by dk, which we derived in the last but second lecture, this d omega by dk is proportional to the sound velocity. It is actually the sound velocity v sub s, and this velocity is of the order of 1000 meters per second. I mean, it could be 4000, 5000, something like that. In air, you know, the velocity of the speed of sound is of the order of 300 meters per second, and this number on the other hand is of the order of 5 orders in magnitude larger, the speed of light compared to the speed of sound. So, if you draw this dispersion, omega equals ck over here, it will look like this. So, it will be a line which is very, very steep and which will cut the optical axis at some point over here. Well, because of the structure of the optical line, because it's a continuous, quasi-continuous line which goes like this. So, no matter howsoever steep the blue line is, it's always going to cut the optical axis, and because the omega minus branch is too low lying, therefore, the blue line will never cut the omega minus branch. Okay. So, what does this signify? What it signifies is that if you draw over here this blue line, which is the dispersion for electromagnetic wave, it's going to look like this. It will be almost a vertical line going very close to the omega axis. So, this line has no intersection on the dispersion whatsoever. On the other hand, in this case, the blue line has a dispersion on the omega plus branch. What does that mean? At this point, which is yellow point, at this point, the wave number and the frequency of the electromagnetic wave and the wave number and the frequency of the lattice wave are matching. And this matching is very essential, very important if you want electromagnetic waves to interact, to have an interaction with the lattice. So, for the lattice light interaction, or for the lattice crystal light crystal interaction or crystal matter interaction, it is important to have this upper branch, omega plus branch, all right. And it is for this reason that we call the omega plus branch as the optical branch. So, it is called optical because it gives you an access to investigate the interaction between the light and matter. So, the light interacts with matter. So, what that means is that a quanta of electromagnetic radiation can actually excite lattice waves in the crystal, but that can happen by the virtue, only by the virtue of having this kind of a mode which has a non-zero value at k equal to 0, and such modes from now onwards will be called optical modes. Okay. So, this is an optical mode. So, we stop here. This is the first part of the lecture. Now, we will go to the second part of the lecture. So, let us go back to the monatomic chain because it is simpler to deal with, to get to the second part of this lecture. We have derived the dispersion and we talked a bit about the interaction of light with the matter, with the crystalline lattice that would happen by virtue of the optical branch, omega plus branch. But besides that, we have to use the vibrational properties of the solids to understand its very many physical properties. For instance, the specific heat of solids, right, and the thermal conductivity of solids, which is which has a significant contribution from the lattice vibrations. So, in order to understand these, we have to develop a new language, and the purpose of the second part of this lecture is to introduce you to this new language. Suppose I have to write the Hamiltonian for this chain, for the 1D monatomic chain. So, the Hamiltonian will consist of the kinetic energy term, which is half m x dot square, and suppose you are writing it for the nth atom. So, it will be x subscript n dot square, okay. And then if you sum it over all the n's, that will give you the kinetic energy for all the atoms in the chain. But you should also add to it the potential energy, or the energy stored in the springs, okay. And that energy is given by half k x square. But these are coupled oscillators, so you cannot write it simply as half k x square as you would write for a single oscillator, where x is the position of the oscillator from its mean position. You have to take into account that each oscillator has an oscillator to its left and to its right, with whom it is connected, interacting in so to speak. So, therefore, the potential energy term should be written as x n plus 1, all right, minus x n whole square, right. So, taking into account the neighboring, and this n will run from the first atom till the nth atom, and here you will run into capital N plus 1. You will invoke the periodic boundary condition and write it as x1, all right. So, this is the Hamiltonian of the 1D chain, monoatomic chain. The problem with this Hamiltonian is that it has the cross terms like xn plus the product terms like xn plus 1 times xn. Right? Such terms are present here. So, here in the Hamiltonian there are product terms. For example, in this one you will get xn plus 1 times xn, right. And these terms are there because the springs are coupled to each other, because this is the Hamiltonian of a coupled, because 1 is equation 1 gives the Hamiltonian of a coupled harmonic chain. So, these are all coupled to each other, and because of that coupling you get these product terms, okay. Now, suppose you want to get rid of terms like these, what should you do, and whether it is possible or not to begin with. So, the thing is that in your Hamiltonian they are only quadratic terms. So, the first term is quadratic in x dot and the second term is quadratic in the position vectors, okay. So, it would be very much possible to actually remove the cross terms by doing a coordinate transformation. For example, if you have the equation of an ellipse which is written not in the xy coordinate, which is written in the xy coordinates, but suppose the major and the minor axis of the ellipse are not coinciding with the x axis and the y axis, in that case the equation of ellipse will also have the cross terms like xy, for instance. So, it will have x square, y square as well as xy. If you make a coordinate transformation which in this case would involve rotating the coordinate frame, and then you rotate it until the major and the minor axis of the ellipse coincides with the frame. And then in the new transform basis, the equation of ellipse will have x square and y square terms alone, will not have any product term. Okay. So, a similar transformation can be carried out over here, and you can transform this Hamiltonian into one where the coordinates are so written that you do not have the cross terms. Okay. Now, this can be appreciated better if we take a simpler example. We should first try to see why is this transformation possible in the present case. So, if you look at a simpler problem, a problem which you may have seen in fact in your first or second year mechanics course. So, there is a spring and a mass and the spring, mass and the spring. So, this is the simplest, so to speak, two body coupled problem. Let us assume that the masses are equal, so they are mm, and the spring constants are also equal, so they are k, k, k. Okay. In this case, you can very easily show that there will be two normal modes. Of course, there will be two normal modes because there are two oscillators in the system. Right. In a system of n oscillators, you have n normal modes. I am talking about the 1D world in 1 dimensions. So, here you have two normal modes. So, what are these normal modes? What are their frequencies? So, the normal mode 1 is omega subscript 1, and its frequency is simply under root k by m. This you may have derived in the first semester of first semester or second semester, whenever the mechanics course comes. And the second normal mode corresponds to omega 2, which is equal to under root 3 k by m. Now, in the first mode, both the oscillators oscillate with this frequency. In the second mode, both the oscillators oscillate with this frequency. In the first mode, the oscillators are moving completely in phase, and in the second mode, the oscillators move 180 degree out of phase. All right. So, the first mode is where these two atoms are moving in phase. So, they will move together sidewise like this, back and forth. So, the middle spring will remain relaxed all the time. They will move together to the left and to the right, and so on and so forth. So, that is the mode 1. The mode 2 is when the two atoms are moving out of phase. So, they will come like this. So, the spring in the middle will get compressed, the springs at the ends they will get stretched, and then it will move out where the opposite will happen, and this will have a higher frequency because all the three springs are in action, they are active. So, it has a frequency of 3 k by m. So, these are the only two modes that are there in your system. Now, any general motion that you can start here by giving various different initial conditions can be written as a superposition of these two. Okay. So, for instance, for any general motion, we can write the position of 1 at any time t will be given by a1 cos omega 1 t plus phi 1 plus a2 cos omega 2 t plus phi 2. And the position of the second atom expressed in terms of normal modes. So, these are the normal mode frequencies, will be A2. So, it is a linear superposition. So, in this case, you have added them, and in the second case, it is just the subtraction of the two, omega 2 t plus phi 2, where phi's and a's are determined by the initial condition. What the initial conditions are will decide what should be phi and what should be a. So, you do not have to worry about that. The important point is this: these are the normal frequencies frequencies of the normal modes of the system. Now you see what we can do here. So the motion is coupled. If you look at it in terms of x1 and x2, these two oscillators, their motion is coupled, which is very much reflected over here in the structure of these two equations. However, what you can do is you can do a coordinate transformation, and you can go from x1, x2 to a new basis. Let's call it a q basis. So you can define two new coordinates. One is q1 and the other one is q2. And let's say q1 is simply x1 plus x2. So if you do x1 plus x2, what would you get? If you take x1 plus x2, these two terms are going to get cancelled, and you will get twice of a1 and then cosine omega 1 t plus phi 1. And similarly, q2 is x1 minus x2. We define it this way, and if we define q2 in this way, the first term is going to get cancelled, and we will get twice of a2 time cosine of omega 2t plus phi 2. Now, what have we achieved? If you look at the structure of q1, what does it look like? q1 is equal to some amplitude time a cosine wave. It's a simple harmonic oscillator. If you look at q2, it's a simple harmonic oscillator. So what have you done? You have reduced a problem of two coupled oscillators by going into a new basis, which is known as, this basis is known as normal, or these coordinates are known as normal mode coordinates. So from this frame of reference, the whole motion looks like as the motion of two uncoupled oscillators, uncoupled or decoupled. So you decoupled them basically. So let's use the word decoupled. So two decoupled oscillators whose positions are given by q1 and q2, which is given like here, two decoupled oscillators. Okay. So the same philosophy can be invoked over here, because this is also a system where you have n normal modes starting from omega 1 to omega n, right? A bit more complicated than this. Instead of 2, you have a system with n particles, n masses. The boundary conditions are slightly different, but that doesn't change the broader picture. So therefore, what you can do then is that you can invoke a coordinate transformation. So you can go to a basis of q's, okay, where some q, let's say q sub s, will be written as a combination of the x's. Like here we wrote q1 equal to x1 plus x2. So here your q's will be written in terms of your regular coordinates. So it will be something like a1 x1 plus a2 x2 plus a3 x3 and an xn. So you can write it as a summation over let's say we are using s, so we have to be consistent, and then you have these coefficients. So the coefficients are s, let's say m, and then you have xm. Sorry, so this should be then m. This is your runnings index. So you put m equal to 1 to capital N. So these are your x1, x2, x3, and these are the coefficients. So that will be for q1, for instance, when you put s equal to 1, and same for q2, q3, q4. You can write it in terms of column vectors, and A in terms of a matrix, and then x is again in terms of a column vector, x1, x2, x3, xn. So therefore, this matrix A, so I'm going to write it as A tilde. So this is, A is the matrix of transformation that helps you in transforming the x, the basis x to the basis q, transformation matrix basically, which you can use to go from the x basis to q basis. So, you can go from the basis of q vectors to the basis of x vectors and the opposite, of course, using A or A inverse, using the matrix A. So, if you, you know this better than me. So, if we use these coordinates, what are these coordinates called? These are called normal mode coordinates. If we use these coordinates, then your Hamiltonian above, the Hamiltonian in equation 1 will get much more simplified. It will not have the cross terms. So, it will just have q dot n square plus qn square, all right. So, let me just write it then. So, it will look something like this. The Hamiltonian in the transform basis will be summation over n half q dot n square plus omega square subscript n q n square, right, where masses and the spring constants are taken care of in omega. So, what is this? These are your capital N decoupled simple harmonic oscillators. You could do this because of the fact that you're dealing with a system of normal modes. Simpler example is over here. This is a huge simplification. I mean, I don't know I should call it a simplification or not. Definitely it's a simplification, and it is going to take us into will make us use actually a new vocabulary, a new grammar that we are going to invoke. So, now we have oscillators. So, corresponding to the frequency omega 1. So, remember omega 1 is the mode, the first mode, then you have the second mode, then you have the third mode, and in your system altogether you have n modes. So, corresponding to omega 1, you got a normal coordinate, you got coordinates q1, q2, q3, q4 and so on and so forth. Okay. And give me a minute. So, so corresponding to omega 1, there is this harmonic oscillator, which is q1 dot square plus omega 1 square q1 square, all right. So, what are the eigenvalues of this? Now, this is a quantum harmonic oscillator because you are dealing with atomic masses, right. So, the eigenvalues of this would be n1 plus 1 half h bar omega 1. Similarly, for this one, you will have n2 plus 1 half h bar omega 2 and so on and so forth. Okay. So, what is n1 over here or n2 over here, or in general n subscript s for the sth mode? These n's, you know these n's, you are familiar with quantum harmonic oscillator, and you know that these n's can take values such as 0, 1, 2, 3 and so on, and the values that they take tells you which excited state the harmonic oscillator is exploring. So, for instance, when n is 0, then you know that the harmonic oscillator is in ground state. Okay. So, in our case, in our language, this n is a quanta of oscillation. So, we will say that n1 is a quanta of oscillations of the normal mode 1. Okay. Similarly, n2 is the quanta of oscillations or vibrations of the normal mode 2, and so on and so forth. Okay. And this quanta of oscillations, this is what we are going to call a phonon. So, this is a phonon. So, when n is 0, there are no phonons. When n is 1 phonon, because there is one quanta of oscillations. When n is 2, there are 2 phonons. There are 2 phonons that live on mode 1, and then n2 can be 1 or 3 or 5, and then therefore you know how many phonons are there corresponding to the mode 2 and to the mode 3 and so on and so forth. So, what does that mean is that now the chain, the system that you have is a system consisting of n decoupled harmonic oscillators, and if you have to describe the quantum state, the vibrational state of the system in general at any time t, what would you do is, so you will say that the vibrational state, which is a quantum state, so vibrational quantum state of the chain will be completely specified or completely known if we know what? If we know this set, if we know what is the value of n1, if we know what is the value of n2, n3 and so on and n. If we know these numbers, then we know the vibrational state of the chain. So, basically the whole game is now reduced, the whole problem has been reduced to finding these numbers or knowing these numbers. So, what determines these numbers? What controls these numbers? So, these numbers are actually, I mean, by numbers I mean the quantum states of various harmonic oscillators, whether they are in the ground state or whether they are in the third excited state, will be determined in a system. It will be determined by the temperature of the system. At 0 temperature, for instance, all the modes will be living in the 0th state. So, there are no phonons. And now you start cranking up the temperature. Suppose you have a knob that controls the current flowing through the heater, and your 1D crystal is placed in thermal contact with this heater. So, you start increasing the current passing through the heater, that will heat up the heater and the 1D chain, and therefore, you will excite more and more phonons. What that means is that the mode 1 is the mode which has the lowest frequency. So, the mode 1 is the mode which lives here at the center of the first point from the center of the build 1 zone. The center is at omega equal to 0, the first point, and then omega 2 is the second mode, and so on and so forth. So, as you increase the temperature, what you do is you basically start populating these modes. You give some non-zero value to n1 and then to n2 and then to n3 and so on and so forth. So, at some temperature, let us say the temperature, so this is omega axis. If you multiply omega with h bar, what you would get is energy, right. So, this is also the energy axis if you normalize by the Planck's constant. So you can write the room temperature energy. So let's say at room temperature the energy scale is here. So let's say this is your kBT, where kB is the Boltzmann constant, T room, okay, which is 300 Kelvin. So let's say this is the energy. So if the thermal energy is this much, then what that means is that the modes that are below this energy would be excited to higher values of n, right? We don't know what values of n the system would explore. Maybe n is 25, maybe 28, maybe 23. We don't know that. And as you go up, so as you go above this energy, as you go to higher energies, so you're going up in energies as you're going up here. The modes that live here, they will be lesser and lesser excited, which means that the probability of these modes having the quantum number n equal to 0 is much higher, because the energy is much higher compared to the energy which is available to the system. So what governs the values of n's is what we are now seeking, what we are trying to derive. Sorry. So, so let's do that. So at any temperature, so you know at 0 temperature, the state of the system is given by 0, 0, 0, 0, 0. But suppose the temperature is finite. So at any temperature T, at any temperature T, you can write the state of the system as follows. You can say that your N1 can have any value. It can be 0, or it can be 1, or it can be 2, or it can be 3, and so on and so forth. Same for N2, 0 or 1 or 2, and same for the other n's. So the state of your chain will be N1 has a value, let's say 6, and N2 has a value, let's say 8, and N3 has a value which is, let's say 4, and so on and so forth until you have reached n sub n, right? So that is the state of the system at any temperature T, right? For example, it could be that your mode 1 is at 3. So maybe this is 3, maybe this number is 4, maybe this number is 2, and maybe 1, and maybe 0. Maybe the temperature is too low, so maybe all the higher modes are nearly 0. That can be one state, one quantum state. So now we can write the energy, the vibrational energy U of the chain. So now, of course, you have seen the complexity of the problem yourself, that you have first of all a large number of quantum numbers to deal with. So n1, n2, n3 are the quantum numbers of the problem, and you have capital N quantum numbers to deal with, and each of these quantum numbers can take infinite number of values. There are infinite possibilities. It can be from 0 to infinity. So you're dealing with a problem which is truly a many-body problem. So in this case, what we are going to do is to use the statistical mechanics to calculate the average energy U of the system at any temperature T, all right? And we are going to find out, in fact, the intent of doing this is to find out how these various states will be distributed, in the sense how the temperature will decide what the N1 should be or what the N2 should be, right? So you'll see that in a minute. So you can write the energy U as sum over S ES exponential minus beta ES. You're familiar with this, I believe. Summation over S exponential minus beta ES. This is one of the most common things that you do in statistical mechanics, find out the partition function, and then the average energy is given by this, where the factor over here, this is actually the probability of finding the system in the Sth state. So, S here is the quantum state, and the quantum state is given by this. All right. So, let's try to write U. So, in order to facilitate this calculation, to make this calculation easier, so we define a quantity f, and don't ask me what f is, because f is just a facilitator. That's why probably I'm representing it by the letter f, and it's going to help us in evaluating u, in calculating u. So, f is defined as ln of summation over s. Yeah, so this is defined like this, exponential minus beta e s, and you can readily verify that u and f are related. How are they related? Pause the video for a minute and try to see what's the relation between f and u. You would see that u is nothing but partial derivative of f with respect to beta with a negative sign in front. So, u is just given by minus del f del beta. So, once you have computed f, you can in principle get u just by taking the derivative with respect to beta. So, let us try to compute f for the quantum state S, which is given here. So, this is the state, quantum state S of the chain, right. So, let us write f. So, it will be ln and then the state 1. So, that would be exponential. So, n1 can be 0. So, that 0 corresponds to exponential. So, when n1 is 0, the energy eigenvalue will be, when n1 is 0, the energy eigenvalue will be 1/2 h bar omega 1. So, that is E1. So, therefore, it will be minus 1/2 beta h bar omega 1, or n1 can be 1. So, or n1 can be 1. So, therefore, e to the power minus 3/2 beta h bar omega, or n1 can be 2. So, that will give you the next term. So, this is my first bracket where I have replaced ors by the plus sign, because that is the rule how you add various possibilities, right. Now, we can have any of these and any of these. So, this and here will be replaced by a multiplication sign, and then you get a second bracket, and this second bracket will be for omega 2. So, here you have omega 1s, and then you write it for the omega 2. So, exactly the same as this one, but this is for the mode 2 or omega 2, and then you again put a multiplication sign and then write it for omega 3 and so on and so forth. So, that is the expression for f. Now, what do you see here is you have this ai, so let us call it a1, and then this is a2, and then this is a3. So, it is a product of all these terms a1, a2, a3, a4. So, we can as well write it, because it is log of a1 into a2 into a3. So, we can write it as log of a1 plus log of a2 plus log of a3. So, we can then therefore write it as summation over some index I, and then log of exponential minus 1/2 h bar beta omega I plus exponential minus 3/2 beta h bar omega I, and so on and so forth. Okay, so you put I equal to 1, you get the first bracket. You put I equal to 2, you get the second bracket, and so on. Okay. Now, this is a series, a geometrical progression whose first term is here, and the common ratio is e to the power minus beta h bar omega I. So, therefore, you can sum it up, using the geometrical progression series. So, you get summation over I ln, and then exponent, first term is exponential minus 1/2 beta h bar omega s divided by 1 minus the common ratio, the ratio of the progression, which is minus beta h bar omega s. So, that is the expression for f that you have obtained. Now, we take the derivative with respect to beta to get u, to get the quantity over here, which is of interest to us. So, to get u, you take the derivative and do the simplification, and because of lack of time, in the interest of time, I am going to write the result directly. So, you are going to get something like this, summation over I, and then 1 over exponential beta h bar omega s minus 1 plus 1/2, sorry, this is I, h bar omega I. Now, I can call this as this prefactor as Ni. So, then the energy, the vibrational energy is just N subscript I plus 1/2 h bar omega I, which is what you had expected in the beginning, because you see your mod 1 has this energy, mod 2 has this energy. So, therefore, you will write the total energy of your system as the sum of these energies, right. So, it has to be the sum. So, it has to be what is the value of N1, and then you write the energy, and then for N2 and for N3. But what have you learnt by doing all this jugglery is that you got an expression now for N, for Ni, and the expression is over here. Right. So, that is the reason why we worked so hard. So, we now have an expression for N, for Ni, which is omega I minus 1. So, Ni is a function of temperature, as you can see here. For a given mode, Ni depends only on temperature, and for a given temperature, Ni depends on the mode energy that you are talking about. H bar omega I is the energy of the mode. So, if you fix the temperature, let us say you fix the temperature over here, then the distribution function, this is known as the distribution function. So, here is the distribution function for the quanta of oscillation, which we called phonon. So, it is a distribution function for phonons. All right, this is the distribution function for phonons, and this actually gives you how the phonons are distributed amongst various modes at any given temperature, or how the phonons will be distributed as a function of temperature for a given mode, for a mode I. So, that is the beauty of it. And this expression that we have derived here in the context of a 1D monoatomic chain is actually a very general expression. It is valid for, in general, this is known as the Bose-Einstein distribution, or the Bose distribution rather, and this distribution actually is valid for all the bosons, the particles that have spin 0 or integral spin. So, for phonon, the spin is 0, it is a spinless particle, but a photon is a spin 1 particle, it is a boson, and for photon also you use the same distribution function, and in fact, you may have unknowingly used it when you were deriving the Planck's relation in the context of electromagnetic waves. So, in the next lecture, we are going to take this further. So, just to summarize 2 minutes, what we have done, what we have achieved is the following. We had n normal modes, The normal mode frequencies are given by omega 1, omega 2, omega 3 and so on and so forth. So, because we are dealing with the normal modes, we went to the, we did a coordinate transformation and we went to the frame of reference where we are using normal coordinates, and in the in terms of normal coordinates, we could decouple this Hamiltonian and write it as a sum of decoupled harmonic oscillators. So, corresponding to the mode 1, these are the energies of the oscillators, quantum oscillators. Corresponding to omega 2, these are the energies, and once we had this, then the total energy would be simply given by this expression, which is summation over I Ni plus 1/2 h bar omega I, where Ni is given by this factor, this distribution function, which we derived in this lecture. And this process of coordinate transformation, which I had put very naively as coordinate transformation, the process of going from here to there is actually a more tricky process, which we did not discuss here because of the mathematical complexity that it involves. So, this process is actually known as the second quantization. So, what you have done actually is you have quantized the lattice waves in terms of simple harmonic oscillators. So, second quantization, and what you have done is you have quantized the lattice waves, and the quanta of a lattice wave is called a phonon. So, that is what we have learned. So, this is the new language that we have developed, the language of phonons. So, we can now talk in terms of phonons. Right? I will tell more about the phonons in the next lecture. I think we can stop here. Thanks.